So the basic rule is never install the first version, the X.0 or N.0 version of the software, but wait for the N.01 version to come out. This is always going to be problems. But anyway, I thought I would show you this picture of an impala, which is one of the most common antelope in Africa, and it's actually quite a beautiful animal. And lots of other pictures here. And in your textbook, you'll see there's one picture as well. Later on, I'm going to talk about turtle excluders, which are devices in the ocean that allow turtles that get caught up in fishing gear, like nets, to escape out of the side of the net, whereas the fish, for some reason, can't do this. So actually, there are requirements that the National Oceanic Atmospheric Administration requires and regulates fisheries to make sure that they don't catch turtles and they don't catch dolphins and these sorts of things. And they're very stringent requirements related to the ability to catch these animals in what's called bycatch, by-catch. So I'm going to have to, it seems, close this. Let's just see, because I can't move it. Okay. So one of the things you have in Africa, particularly in South Africa, is sometimes people establish ranches. You have this in Texas too, and other parts of the U.S., where you get game ranches, and the meat of deer or antelope, or even bison, anybody had a bison burger, are produced for the general market. The meat's supposed to be healthier because it's not pumped with hormones, it doesn't have as much fat. So there's an individual by the name of Piet Meyer, which is a typical South African name, P-I-E-T, which of course the English equivalent is Peter, who's a game rancher, and he plans to establish a population of impalas on his ranch by introducing a certain number of immature females and mature females. So we're going to use X to represent the immatures over here, and Y to represent the matures. And since production comes through the females, you can also have some males, you have to have a certain number of males around, but if you're interested in producing new young, you certainly don't need a 50-50 sex ratio. And Pitt talked to other farmers around, or ranchers around the country, and he found out that he can expect each female to produce on average 1.2 new females every 2 years. So the basic interval of time that we're going to iterate is every 2 years. And he expects that each female, that 40% of these females will survive to age 2, at which time they start to reproduce, and that once they're adults, 20% of them will die in each time period every 2 years. That means 80% will survive each 2-year period. So again, we're going to have a model where we have juveniles and adults, and we're going to look at the females, and we're going to project how the population will grow from some initial starting values. So what happens if Pete initially buys 100 immature females? In 10 years, how much production can he expect? Or should he buy 50 immature females and 50 mature females, because mature females are much more expensive? So he can run the numbers, but he wants to project out the population. So how many adults can he expect on his ranch over the next 6 years? So if you're iterating every 2 years, that means they're going to be for the next 3 time periods. And discuss how the situation differs from the expected outcome in scenario B. So we're going to compare what happens if he starts out with 100 immature females versus 50 immature females and 50 mature females. So the first thing we have to do is write out an equation, and we say let xn over here be the number, and yn be the number of immature females and mature females, respectively in time period n, which corresponds to year 2n from the start, because these numbers apply every 2 years. Okay? So if we read the problem, then we see that the number of new juvenile females in time period n plus 1 will depend on the number of mature females in time period n, and we are told that each mature female is expected to produce 1.2 immature in that time period. So we have xn plus 1 is equal to 1.2 yn. Everybody happy with that? And now what about adults in time period yn plus 1? We have a certain number of adults in time period n, and we expect 80% of them to survive, and we expect 40% of the immatures from the previous time period to survive. So that means yn plus 1 over here is equal to 0.4 xn plus 0.8 yn. Everybody happy with that? Okay? Now we can write this in vector notation. In your textbook this is correct, but these notes were prepared prior to the textbook being corrected. So there's a number 1.2 there, but this number should actually be 0.8, but it's correct in the textbook. But if you're working from your notes, just make sure you correct that. Beg your pardon? This number should be 0.8. In the textbook it's correct, because when we did the final version of the textbook, we went through and picked out all the mistakes, or almost all. But this was made from a pre-version of the textbook, and I actually don't have the final files that we corrected. So this is if you write it down in notation, and remember we said we're going to write equations in the form of a vector. So here we've got a vector u, which has elements x and y. We've got a matrix A, which has got 4 entries. And so you can write this as u at n plus 1 is a times u at n. If you stick to the rules of vector notation, then this formula over here is equivalent to these two equations over here. Okay. So now, in order to find out how many individuals we have at some arbitrary time in the future, we write the equation u1 is a times u0. And if we start off with, in this case, if we start off with 40 adults, then, in this case, if we start off with 100 immatures, so there we're starting off with 100 immatures and no adults, and we do this multiplication. If you remember, to multiply, we multiply this term by that term, and then this term by that term. So we get 0 times 100 plus 0 times 1.2, which is 0. And then this term, 0.4 times 100 is 40, and 0.8 times 0 is 0, so we get 40. So what happens is the 100 immatures have become 40 adults. And there were no adults around here to produce new matures, so we don't have new matures, so we don't have any new immatures. So now we've got 0, 40, and we want to calculate U2. So we're just iterating this formula. First we start out at U0, which gives us U1. Then we start out at U1, which gives us U2, and we keep multiplying. So it turns out that U2 is going to be 4832, U3 is going to be 38.4, 44.8. So of course that's a problem, because what does it mean to have a fraction of an individual? So these models produce fractions of individuals, but also these models don't take into account stochastic processes that affect the number of actual births. So if you say the expected number is going to be something, then the actual number comes from a distribution. It's like if I flip a coin 10 times, I expect to get 5 heads and 5 tails, but sometimes I'll get 4 heads and 6 tails. So this is called demographic stochasticity. Later on in this course, we're going to work with models that allow for that stochasticity. In this case, the model doesn't allow for the stochasticity, so it's ignoring the fact that there is this demographic stochastic effect. But you can just round it off if you want, or you can treat these as averages in measuring densities in a much bigger system, where these may be densities per square kilometer of ranch land or whatever. Now, as you go through this, you'll see that you get a bunch of points that you can plot in XY space. So we started at 0, 100. That took us to, 0, 100 took us to 40, 0. So we started off with 100, 0. That took us to 0, 40. Then 0, 40 took us to 48, 32. So we went from there to there to there. And then if we plot the next point, which is 38.4, 44.8, then we jump to there. And then the next point we jump to here, then we jump to here, and then we jump to here. So what seems to be happening? What's the behavior of the system in the plane? What does it seem to be doing? Yeah? Well, it seems to be approaching not an equilibrium, but a line. An equilibrium is a point, but it's approaching the line. So it's a little more, but I mean, that's the basic idea. It turns out that it's called an equilibrium distribution because it's two values, x and y. What's in equilibrium is the ratio of x to y. The ratio of x to y is the slope of this line. But the population is actually growing, but it approaches that ratio. Now let's start off on that line. If we start off with x0 and y0 equal to 50, so I'm saying to you, what happens if I start off at this point over here, which is 50? You'll see then I go to 60. So I start off at 50. If I start off at 50 and I do this multiplication, I get 60. If I'm at 60 and I multiply and I iterate again, I'll get to 72. And if I'm at 72 and I iterate, I'll get to 86.4. And what you can see is that the population is growing, but the ratio of x to y remains the same. And it acts as though the population is being multiplied in each time step by 1.2. So if I start at 50 and I multiply each of these by 1.2, I get to 60. If I start at 60 and I multiply by 1.2, I get to 1.2 squared times 50, which is 2.4 times 1.2 squared, which is 1.44 times 50, which is 72, and so on. And in general, the solution, if I keep multiplying, behaves like 1.2 to the n times 50, 50. Now, here the general solution I can't write down that easily. The general solution I can't write down in a straightforward number, so I can't write down u to the n, because you can see that although it's approaching equal values for its x and y coordinate, they're not quite equal. But if I start off with equal values, then I have this very simple way of writing down a general formula for the nth time period. So as long as I start in the right place, I very simply have a simple formula, which is just 1.2 to the n. So the population is growing in each time period, here, by a factor of 1.2, and it seems to be staying on that line. Does everybody understand that? So it turns out that there exists a vector, v, let's say, such that if v has equal values for its x and y components, let's call them c, and if I call them c, then this is also equal to a scalar c times 1, 1. We c is any positive constant we like. And in this case, for this particular model, c turns out to be 1.2. Then the population grows as though the initial vector is multiplied by a scalar instead of having to multiply each time by a. So if I set up this equation, what I'm asking is there some vector v? In this example, the vector v was 1, 1. Is there some vector v such that a times v is equal to some lambda times v, where this, in this case, is a matrix, and in our example, it's 2 by 2, and this is a scalar, so it's just a number. So that's the question I'm asking about. Can I find some vector v such that if I start out there, multiplying v by the whole matrix A is the same as multiplying v by just a single number? Does everybody see how that worked in the last example? So the question is, how could you solve such an equation? Now, if there is a solution, so if solution, then lambda and v are called the eigenvalue and eigenvector. Now, part of the problem of why this is scary is because it has this strange name. In mathematics, we often call it the eigenvalue and eigenvector, but sometimes we translate it from the German, and eigen means characteristic. So if you look at English has got a lot of French words and German words and all sorts of things like that, and especially when we come to technical things, sometimes we keep the word without translating it. So if you look up and you say characteristic values, eigenvalues, same thing. And you might prefer characteristic. So these are characteristic because a characteristic of this model is that no matter where you start out, if I start out here, or I start out there, or I start out there, I'm going to grow in such a way that I approach this line, and once I'm near the line, I'm going to grow at a rate 1.2. So I'm going to head in the direction of the defined by the eigenvector, and I'm ultimately going to grow by an amount that's given by the eigenvalue. So in order to understand what's going to happen in the long run, it doesn't matter where you start. The system, in the sense, ultimately forgets where you start. The long-term behavior is just characterized by these characteristic directions and growth values. This doesn't, if lambda is less than 1, then actually you're going down instead of going up. So remember we said that if you're on the line and you multiply by a point, by a number less than 1, then you'll move down. If you multiply by a number greater than 1, then you'll move up. Okay? Any questions? So now you'll find in the textbook there are a number of examples of how to solve this problem. If I tell you what lambda is, can you find v? Or if I tell you what v is, can you find lambda? So here's a matrix, and I'll say that it has two eigenvectors. One of them is 1 and 3, and the other is 2 and 3. So when you look at a thing like this, you say, how many solutions are there? It turns out that if this is a 2 by 2 matrix, there are generally 2 solutions. If it's a 3 by 3 matrix, there are generally 3 solutions. If it's a 4 by 4 matrix, there are generally 4 solutions. How this comes about, we'll see as we work through the 2 by 2 example. And so what you have to do is you have to apply the formula, and we say, okay, if I take my matrix A, and I'm told that this is an eigenvector, when I multiply it, I get 2 and 6. I started off with 1 and 3. So that just by inspection, I can see that basically I've taken 1 and 3 and multiplied it by 2 to get 2 and 6. So if the eigenvector is 1 and 3, and I do the multiplication, just by inspection, I see the eigenvalue must be 2. If the eigenvector is 2 and 3 instead of 1 and 3, and I do this multiplication, then I see I get 6 and 9. 6 and 9 by inspection is equal to just 3 times this and 3 times that. So that's equal to 3 times 2 over 3. So that means if this is the eigenvector over here, then the corresponding eigenvalue is lambda equal to 2. If this is the eigenvector, then the corresponding eigenvalue is lambda equal to 3. So that's pretty simple. Now I'll go the other way around. I'll say, suppose I've got an eigenvector which I don't know what it is. I've got x and y. But I know that its eigenvalue is 7. So then I can say the equation is A times the eigenvector is equal to 7 times the eigenvector. And if I do that, when I multiply this out, I get 7x equals 7x, and minus 8x minus 1y is equal to 7y. I can then solve this, and I see simply that this means x must be equal to... Well, if you have a look at this, the interesting thing here is that any value of x will solve this problem. So you can just choose one. The most convenient value to choose is x equal to 1. X equal to 2 will do equally well. X equal to 3 will do equally well. This may seem like a little bit of a mystery to you. It'll become clear in a minute. So I choose a value, let's say x equal to 1, and then I solve this equation with x equal to 1. And then, if I solve this equation, I'll be able to express y in terms of x, and if I set x equal to 1 in this equation, then I'll get minus 8 minus y is equal to 7y, which means y is equal to minus 1. So that means if I take a, and I multiply by 1 and minus 1 vector, I'll get 7 and minus 7, which is 7 times 1 and minus 1. So you'll see that I know that 7 is my eigenvalue, so that 1 is an eigenvector. Now what would happen if I had chosen x equal to minus 2? Or x equal to 2. What I would have got here was 2, and I would have got minus 2. I would have got exactly the same proportion of x to y. So what is uniquely determined is the proportion of x to y. And what that says is that an eigenvector is unique in terms of its slope. But any point on the slope, on that line, will define it. So in this case, 1 and 1 will tell me it's basically got a 45-degree angle, or 40 and 40, or 60 and 60. So the eigenvector is not unique. It only has a unique direction. And the reason why it's not unique is that the solution is not a point in space, but a line in space. Does everybody understand that? This is very important. When you solve the eigenvalue and eigenvector equations, the eigenvalue is such that it will cause the two equations that are set up to actually be multiples of one another. And in that case, you don't really have two equations, you only have one equation. And what is unique there is the relationship between x and y. So what is unique is the relative value of x to y, or the relative value of y to x, whichever one you select first. And that then will define a direction, but it won't define a point. Has everybody got that?